Alright, so let's begin to put the quantities we were talking about before together. So we're going to link voltage, current, and resistance, and they all are related by Ohm's law, which is this equation here, V equals IR, where V is our voltage in units of volts, I is the current in units of amps, and R is the resistance in units of ohms, symbolized by the Greek letter omega here. So let's go ahead and try a practice problem here using both Ohm's law and also we're going to go back to that mathematical definition of current that we had before. So for the first one, when we're trying to find the resistance of the circuit, we're going to start with Ohm's law, V equals IR. So our voltage here is going to be 120 volts. That's going to be equal to our current, which is this 15 amps here, times the resistance. We, of course, divide both sides by 15. And we find that our resistance in this case is going to be 8 ohms. For the second part, when we're trying to find the current in this circuit, or the amount of charge that flows in the circuit, we're going to start with our definition of current, which is that current is the amount of charge over the time. So we know our current here is 15. We're looking for the amount of charge here, and our time is going to be 1 minute, but we want to put that in units of seconds, so we're just going to put it as 60 seconds. We can go ahead from here and cross multiply those quantities, and what we end up getting is that our charge, the amount of charge that flows through the circuit in 1 minute, is going to be 900, and the units for charge are coulombs, capital C. Let's try one more problem here with this. So we start off being told how much charge flows through a light bulb in 2 minutes. And so once again, using our definition of current, that is the amount of charge over the time, we can figure out what the current is in this light bulb. So it's going to be the amount of charge 19 over our time, but we need to real quick convert that time from minutes into seconds. We probably can just do this in our head. 1 minute is 60 seconds, and so 2 minutes is going to be 120 seconds. But certainly if you need to write out that conversion, you can go ahead and do that. And then we end up finding that the current flowing through this light bulb is going to be 0.158 amps. Using that current, we can then go back to Ohm's law and find our resistance. So we're going to think about V equals IR. So our voltage is 9, our current we just found is 0.158 times our resistance, and we divide by 0.158 on both sides, and we end up getting that our resistance in this case is going to be equal to 56.8 ohms. We're going to add on one additional equation here, and this is dealing with power. And the reason we're doing this, the main reason we're doing this, is that appliances are typically rated based off of the amount of power they use, which is measured in watts. And you'll often hear people talk about, you have a 60-watt light bulb, a 100-watt light bulb. You maybe have a 3,000-watt microwave. You might talk about the power of your refrigerator. And that really is just a measure, if you remember from previous units, of the energy per time. So a watt is really just a joule of energy per second. Okay, that's what a watt represents. The way we're going to find it depends on both the voltage and the current. And the reason for that is the voltage represents the energy per electron flowing through the circuit, and the current represents the number of electrons per second. So when we put them together, we get the amount of energy per second, which is the power. And that leads us to this equation here, that power is just voltage multiplied by current. There are a few ways we can combine this with Ohm's law to rearrange this equation, but I typically just go back to this basic equation. Power in watts is voltage in volts times current in amps. Let's go ahead and apply that equation to a practice problem here. So we have a refrigerator with a power of 800 watts. It's connected to 120 volts, and we want to know what is the current used in that situation. So I'm going to start with the equation we just learned here. Power is voltage times current. And so we can say 800 is going to be equal to our voltage, which is 120, times that current, We divide both sides by 120 here, and we find that our current ends up being 6.67 amps. From there, we want to find the resistance of this refrigerator. The refrigerator obviously is a little bit more complicated than just a basic resistor, but we can still find the equivalent resistance of that refrigerator. And we're going to do that using Ohm's law that we've done many times before here. And so for that, we're going to say that our voltage, which was 120, is equal to that current we just found, 6.67, times our resistance. We divide by the 6.67, and we find that we end up with a resistance here of 18 ohms. All right, one more practice problem here with all these equations. In this case, we are given the voltage of a battery used for a flashlight along with the resistance of it. We first want to figure out what is the power. Well, we know in order to find power, we need to do P equals VI. So we know our voltage, however, we don't yet know our current, which is why we're also going to have to do Ohm's law here. So we're going to say V equals IR. Our voltage here is 6 volts. That's going to be equal to our current times our resistance of 0.5. We would go ahead and divide by 0.5, and we find that the current would be 12 amps. So we can take that and sub that in here, and so we end up with power is voltage 6 times our current of 12, which means we have a power here of 72 watts for this particular flashlight. From here, we want to figure out how much energy the flashlight uses in 30 seconds, and so we're actually going to go back to an equation that we've done before, which is that power is work over time, and we know that work is really the change in energy, so power is going to be the change in energy over time. So we know that our power is 72 watts. We're trying to figure out how much energy is used with that power of 72 watts in a time of 30 seconds. From there, once we have that set up, we can cross multiply, and we find that the amount of energy is going to be 72 times 30, or 2,160 joules of energy over that 30-second period of time. So with this, we will be using this equation our power equation from our energy and momentum unit. So that is an important one to keep in mind. Since we are still talking about power, it still is relevant even if we're thinking about it in terms of electrical appliances. One last little tidbit here, and this is going to be more and more relevant as we move forward. I just want to take a look at this diagram here, which goes through some basic elements of circuits, because we are going to start seeing some circuit diagrams, which is going to be our way of visualizing particular circuits. You don't need to know all of these, and obviously you'll have this as a reference guide, but I do want to point out a few important elements that you'll see a lot. One is this element here, which is a resistor, which is just a squiggly line up and down. Another one that will be pretty common is a bulb, which is a circle with kind of like a little curly Q in the middle. It's supposed to represent the filament. A third one is the battery, which is 2 bars that are not even in length but are parallel. This one is this is a double battery, because we see there's 2 sets of 2 bars. And then the last one that you'll see, and this one's the most basic, is just a conductor. We use that just to represent a wire, just a straight line. So based off of those circuit elements, you'll start seeing circuit diagrams that look something like this. And so you can see things like there's your battery connected with wires. We added in an ammeter here. That's not necessarily one you need to know, but we will talk about that when we're doing labs. That's how we measure current. We see here is a resistor connected to this circuit. The direction of the current is shown there, but that's not something you need to know. But the important piece is you should be familiar with those symbols, because as we move forward, you'll start to see them more and more in our problems.